This is our first problem for our magnetic field, is problem 28.43. We are told that a proton has an initial velocity of 20 in the I-hat direction, and the velocity has units of m meters per second. That big M is saying times 10 to the 6. So we have this as our initial velocity going the I-hat direction. And it enters a uniform magnetic field of magnitude 0.3 teslas with a direction perpendicular to the proton's velocity. This could either mean that the magnetic field is coming straight out of the page or that it's going into the page, right? We don't know yet. We do know that it leaves the field-filled region with a velocity of negative 20 in the j-hat direction. So in the negative j-hat direction, like this, same units. Determine A, the direction of the magnetic field. We know this equation here, this is saying the magnetic force is equal to Q V cross B. We know that the force has to be in the negative j-hat direction because, well, it's forcing the proton down, right? So then we also know that V, the initial velocity, is in the I-hat direction. We know this relationship here, which is saying j-hat is equal to k-hat cross I-hat. But here what we see is that we have negative j-hat. So what we have is negative j-hat is equal to I-hat cross k-hat. This comes from this relationship here, where A cross B is negative B cross A. So that means that the magnetic field has to be in the positive k-hat direction, which is in fact pointing straight up out of the page like this. So the answer is B, is in the plus k-hat direction. Now for B, it says, find the radius of curvature of the proton's path while in the field. We have an equation for that. R is equal to mv divided by qb. Put everything into SI units and all the units should cancel out, right? It's the equation. So we have m, proton, 1.67 times 10 to the negative 27 kilograms. Velocity is 20 times 10 to the 6 meters per second. And then we have all of that divided by Q, which is 1.6 times 10 to the negative 19 coulombs, times B in Tesla, so 0.3 newtons second per coulomb meters. If you again put everything into SI units, it's all going to cancel out, and we are going to be left with R is equal to 0.696 meters. So this is the radius of curvature. C says, find the distance the proton traveled in the field. So let's think about this for a second. We have the proton coming in, and then we have it curving, and we can think of the curve as being part of this circle. So essentially, in black, we have the initial path, and then it's curving like this, and it's exiting as so. So what we see is that it's actually completing 1/4 of this entire circle, right? And we figured out what R is, the radius of curvature, which is this. And we know that there's a relationship between here, the amount of path we covered along the circumference, to the radius and the angle. So we know that S, which is this here, I'll do it in a different color. The path in purple here, that's S. S is equal to theta times R. So S is equal to, where theta is pi over 2, because this has to be in radians here, times 0.696 meters. So this is the amount of actual distance that we traveled along this curved path here. And so S is equal to 1.09 meters. We are then asked to figure out the time interval during which the proton is in the field. To do that, well, we know that this is how far it went. We know its velocity, right? This is how fast it was going. So then we say that, I should know that this is for C. For D, we have delta T is equal to 1.09 meters. That's how far we went per our velocity, which is 20 times 10 to the 6 meters per second. And this is going to give us 54.7 nanoseconds for D.